Hi all. So till now we have studied about the heat transfer, conduction, and steady state as well as transient analysis we have done for the conduction heat transfer. But there is one separate topic that needs to be studied, which is of quite importance for from the practical viewpoint, uh, which is in steady state heat conduction. Actually, the which is nothing but the heat transfer from the extended surfaces. You may have seen that some protruded surface coming out of the engines of a motorcycle like this. So these are the extended surfaces, and let's say this is engine block. So these are the extended surfaces. So these extended surfaces actually are used to enhance the heat transfer from the engine. Okay, so this is one of the example that what is extended surfaces, and these extended surfaces in industry or from academic viewpoint are known as fins. So fins are generally used to increase the heat transfer. But how? But before going into the means of how fins are increasing the heat transfer, first we have to see that how we can increase the heat transfer from any surface. So consider a plain wall. Consider a situation like this. Uh, and suppose this is a surface from, let's say, the engine block, and on this side combustion gases are there which are generating heat. Because of that, uh, heat is supplied from this side and its temperature is rising, and we need to dissipate this heat for proper working of the engine, and also to keep the material within the safe material temperature, okay, of the engine block. So consider that surface temperature means the surface has uniform temperature at, let's say, TB. Why we are calling it is, let's say, it is as base. These are some terminologies which are used in the case of heat transfer through fins. So TB is the base temperature, and let's say this is the surface area of this surface facing the fluid, and the fluid has characteristics of free stream temperature T infinity and heat transfer coefficient H. All right, and so from this surface, the rate of energy transfer to the fluid will be H times A times surface temperature minus free stream temperature. So the question arises, how we can increase the heat transfer, right? So let's say if TB is fixed, so how we can increase the heat transfer? There, in this expression, we can see three ways straight away, right? We can vary the H, A, and T infinity. So we will see one by one each uh, possibility, okay, to increase the heat transfer. So first, let's say about H. H can be increased by increasing the fluid velocity. Okay, so H can be increased by increasing the fluid velocity, but that may not be possible at every time, right? Because when we are increasing the fluid velocity and fluid motion, we have to pay some cost. We have to expend energy, right? And that then the cost we have to pay comes in terms of blower or pump or fan. Okay, so cost will increase if we increase the fluid motion. Okay, so these are the reason that we may not go for increasing H all the time. Okay, because blower or fan on or pump requirement will be there, and it will incur some cost. Okay, to increase the heat transfer, right? So second way is to let's jump to T infinity. Means if we decrease this value, automatically this TB minus T infinity will increase, which will lead to increase of rate of energy transfer to the fluid. Okay, so it will enhance the heat transfer, but changing the ambient fluid temperature is impractical, right? We cannot change the ambient. Okay, it is like we cannot change the season, right? So the third way which is left to us, which is quite practical and also quite feasible, is changing area. So area we can increase the surface area. It means that the surface area which is faced by the fluid of this base surface, all right, of this base surface which is dissipating heat to the fluid. So if we increase that surface area by some means, we can enhance the heat transfer. So how we can do that? So on that surface, what I will do, I will add the material like this, let's say, and if it is not sufficient, I will add more. Per se, this extended surface we are adding to this base surface is of means uniform cross section along the length. Okay, so these extended surfaces will enhance the heat transfer. Okay, and the temperature variation along this extended surfaces is strongly dependent on the material which we are using of these extended surfaces. Right, because we want the heat transfer to the from the fin is H times surface area times temperature at any location. So if this temperature is less than the base temperature, if at any point in the fin, let's say these are many points along the length of the fin and this is base temperature, so we want in ideal scenario that along the length the temperature should not vary too much. So if this location and this location have almost same temperature, then heat transfer rate will be maximum, right? But if, let's say, because we are adding solid material, so what will happen, it will offer some conductive resistance to the heat flowing along this path, so temperature drop will be there. And as temperature drop will be there, this location will not be having the temperature which is so which is having the base, so this location will not be having the same temperature as that of base, so it will perceive the lower temperature because of the conductive resistance offered by this material. Okay, let's say this location had some x location, we are having temperature Tx which is less than Tb. Okay, so how this temperature will vary, right? So it means that in that case Q from the fin at that location will be less than the maximum possible, right? And what is the maximum possible, right? H times A times Tb minus T infinity, right? So heat transfer from the fin is strongly dependent on the temperature variation along the fin, right? And temperature variation along the fin is strongly dependent on, so heat transfer from the fin is strongly dependent on the temperature variation along the fin, which is strongly function of the thermal conductivity of the material. The fin material. And so if thermal conductivity per se is very very high, then the two locations will assume the same temperature, almost same temperature, very quickly, and there will not be a significant temperature drop along the length, right? So it will keep the heat transfer to the maximum possible, means approximately. Okay, so the requirement when we are adding fins is that the fin should have a high thermal conductivity. Fins should always have high thermal conductivity. Okay, so there are different applications of fins which are used in industry, like cooling of IC engines of motorcycles, and lawn movers, and for cooling the electronic components inside the CPU. If you will open your CPU, you will see heat sink like that, which is having